Hi everyone, today we are going to introduce the ConFu system, which helps you find concurrency bugs deeply rooted in your applications. Concurrent software is now everywhere in the real world. Inside these systems, we have a lot of code running in a highly concurrent way. As the real-world applications become larger, it becomes much harder to find bugs. Because, on one hand, we have to cover as much code and control flow as possible. On the other hand, we want to check as many concurrent scenarios as possible from a large state space. To address this problem, we give you the ConFu system. With ConFu, all you need to do is prepare the application you want to analyze. At last, ConFu generates a bug report for you, which includes different types of bugs. Currently, 6 CWE categories have already been supported. From the technical view, the key insight behind ConFu is a combination of schedule fuzzing and symbolic trace analysis techniques. In its fuzzing mode, ConFu generates random schedules by enforcing context switches in a guided way. Iteratively, ConFu leverages stochastic optimizations with runtime concurrency coverage to help generate better schedules. Based on the runtime traces produced, ConFu performs dynamic analysis to identify bugs. When the fuzzing becomes saturated, ConFu switches to a symbolic trace analysis mode. Specifically, it tries to build and solve concurrency constraints and then find unexplored program paths. In this way, ConFu achieves a relatively lightweight and efficient way to detect bugs, while stays aware of the program structure as much as possible. Now, let's check some of the features of ConFu. First, we use these commands to detect data race in the account class. The account class is a demo for a multi-threaded system which manages accounts while keeping track of their internal balance, simulating the bank in the real world. Account array stores the instances of bank account. Each element of account array is started as a thread. The bank account class inherits thread class. It represents the actual accounts in the bank. In the action method, the account will do some service after the sum is randomly chosen. The service method performs the actual action on the account, and it also updates the bank records. In check result method, if the value of bank total are not equal to the value of total balance, the program will throw an exception. Then start the data race detection. The execution results shows there are several data races happen on the bank total variable. You can see, in this case, ConFu finds there are two threads performing read and write operations on the bank total variable. This data race occurs at line 74. Read and write operations are indeed performed at line 74. Since bank total is a static variable, every bank account thread in the program can access bank total without synchronization, which causes the data race bug. Moreover, if we add specific classes into a whitelist like this, and those classes will be ignored during execution. Here, we put account class into the whitelist. Unlike the results before, there were no error messages, which means the account class has been ignored. Next, we can use the fuzzing model tool to iteratively explore the software state space and find bugs in a guided manner. We enable the fuzz mode and set the number of iterations to 20. By the way, we can append a tool named coverage to summarize the code coverage rate. Then the fuzz begins. Let's take a look at the running result. It can be seen that due to the bank record doesn't equal to the account balance, a runtime exception is thrown during execution. Finally, let's watch the coverage results. The defined use coverage of past 20 analysis is shown in a picture. We can see the coverage rate becomes higher when the increase of the iterations. Thanks for your watching.